This is example 2 for the correlation coefficient. We're doing hospital beds. We want to see the relationship between the number of licensed beds and the number of staff beds at a local hospital, in local hospitals. We have an alpha for when we look at our p-value. Let's look at the scatter plot next. We can see when we go from left to right that the dots are actually going upwards. So it's definitely a positive relationship. They're not too close together. They actually seem to be quite the same distance all over the plot. So I would not expect a strong correlation, but we'll see. Let's do the pair of hypotheses. So the pair of hypotheses, we have the null. Remember the symbol for correlation is going to be the Greek letter rho. And the null hypothesis is always equal, so that stays the same. And in this case, it's going to be equal to 0. So what this is saying is that the correlation between x, which is going to be, licensed beds, and y, which is staffed beds, is not statistically significant. The alternative, rho, it's different than 0. So when it tells you that it's different than 0, that means that there's something there. So in words, this would be the correlation between x and y is statistically significant. From here, what we can do is complete the table. So we need to know how many pairs do we have, and in this one I kind of already told you what they were. It's 6 of them. It's not 12. Sometimes I see that mistake. It's just the number of pairs, and that's going to be 6. So we need the sum here, and we can just add them up. That's 12, I believe. These are pretty easy numbers, so that's nice. We add this one. This is going to be 25. Here, what we need to do is multiply across. So 1 times 3, 3, 2, 8, 10, 15, 18. Then we go ahead and add this column up, and that's going to be 56. What we have to do next is for the x, we have to square it. It's supposed to be a little arrow. So 1 square is 1, 1. Oh, let me change the 4, 4, 9, and 9. Then we're going to do the same for the y. So 9, 4, 16, 25, 25, and 36. We add this column up, and that's going to give us 28. We add this column up, and that's going to give us 115. So from here, we can go ahead and plug it into the equation. Now we're going to do the correlation. We need the pairs. So 6 times the sum of x times y, which is this value, 56, minus the sum of x, 12, times the sum of y, 25. All of this divided by a giant square root. Hopefully I can make that fit. Bracket. This is going to be 6. The sum of the x's squared, so that's 28. Minus the sum of the x's, 12. But this one we have to square, close bracket, open bracket. 6 is going to be the sum of the y's square, so that's the biggest number. Minus the sum of y. But this one we had to square it. Oof, I was able to make it fit, hopefully. So let's do this piece first, the bracket. So let's move up a little bit. R is going to be this piece the numerator is 36. Giant square root. This piece that I highlighted is 24. I should be bracket, open bracket. Now let's do this one. So that is 65. Let's use, it's going to use a different color just so it doesn't, you don't get confused. So 36. We're going to multiply those two. We haven't taken the square root, so when we multiply those, that's what we get. So it's going to be 36, and then we take the square root of that, and it's 39.5. We do this division, and that is 0.91. Now we're going to go to the Navarro and Foxcroft. Let me put here, just in case. Scroll way down. So that was our correlation. We're going to use the Navarro and Foxcroft table. So my correlation is positive, and it is in this range. So I can say it's very strong. Positive. Correlation. If we do this in software, we'll also have like a p-value attached to it, so we could add whether it's significant or not.